right? So the next property is of GCD, and this is very important in abstract algebra. Let's see what is it. It tells us that GCD, that is a linear combination. How it is a linear combination? So suppose you are given two integers a and b. Then for these two integers we have two different integers, say s and say t, such that the GCD of a and b could be written as the linear combination of s and t with a and b. So you are writing the numbers themselves, a and b here, and then you have the integers s and t. They could be anything, such that when you multiply them and add them, you will get back the GCD of a and b. And moreover, this is the smallest positive integer of this form, as plus bt. So let me show you how this thing is true. So let's take again the example of two numbers, say a is 50 and b is equal to 20. Then you already know the GCD of 50 and 20, that is 10. So now you have to write 10 as the combination of 50 multiplied with something plus 20 multiplied with something, so that when you add up all of this, you will get back 10. So you see, if you multiply 50 by minus 1, you are getting minus 50, and if you are multiplying 20 by 3, you are getting back 60. So when you add up both of them you will get back 10. So this is how this theorem here works. And we have a corollary related to this GCD whenever we are talking about relatively prime integers. You know, for relatively prime integers, the GCD is always equal to 1. So whenever you know the two integers a and b, they are relatively prime to each other, this linear combination is nothing but equal to 1. So this is the result of this corollary that we are talking about. So if a and b are two integers which are relatively prime to each other, then for those two integers s and t, the linear combination is equal to 1, right? So for an example, if you take 4 and 15, now these two are relatively prime to each other. There is nothing in common between them. So you could write this 4 into something plus 15 into something, and it should come out to be 1. Why? Because according to this corollary. So you could multiply 4 by 4, that comes out to be 16. You could multiply 15 by minus 1, that is minus 15. Add up both of them, so you'll be getting 1. So this thing is true. And suppose now you take two integers which are not relatively prime to each other. Suppose you take 4 and 10 as two integers which are not relatively prime to each other. So in this case, the GCD of 4 and 10 is 2, right? So here the GCD is 2. So now according to the previous lemma, what you are doing, you are multiplying 4 with something plus 10 with something, so that you are getting the GCD of both of them, which is 2. So you are multiplying 4 with minus 2, that is minus 8, 10 with 1, so that is 10. So you, when you add them, you will be obtaining 2, right? So this is what you have as the corollary here. Next, let's move forward and see Euclid's lemma. It tells us that whenever p is a prime number, this is given to be a prime number, and it divides the multiplication of two numbers, then it means that either the prime number is dividing the first number, or the prime number is dividing the second number here. So if p is a prime that divides both the product of a and b, then then either p divides a or it divides b. For an example, you could see this through an example, right? Suppose you have p as equal to 6, right? So here let's take ab as, what can we take? We can take 12 into 1. So you see p divides ab. Why? Because as 6 divides 12, right? So therefore you see, it implies that in this case 6 divide 12, right? So here in this case this is your a, this is your b. So in this case your p divides a, right? So but however this lemma fails may fail whenever p is not a prime number. For example, 6, we are taking this to be not a prime number, right? here I have given you wrong example, because 6 has to be a prime number. It works in this case because we are saying it may or may not work for prime numbers, but it is certain that it has to work for prime numbers, right? So let me give you another example. Here let's take a prime number, let's take P as 5, right? And let's take A as say 10 and B as say 2, right? So then 5 divides 20, that is P divides AB, right? Or in place of 20 you should write 10 multiplied with 2, right? So this implies that 5 divide 10 in this case, that is P divide A in this case, and it fail whenever P is not a prime number. It may fail. So here in this case 6 divides 12, right? 4 into 3, but 6 doesn't divide 4 and 6 does not divide 3 in this case. So this lemma fail whenever it may fail whenever P is not a prime number, right? Next, let us move on to the properties of this prime numbers, which is the fundamental theorem of arithmetic. Now, because primes, they are the building blocks of all integers, so let's see how we can represent any integer in form of primes. So this is given by this theorem, which is the fundamental theorem of arithmetic. It tells us that every integer which is greater than 1 is either a prime number, or if that is not so, then it is a product of primes, and we call them to be the composite numbers, right? So either it is a prime number or it is a product of prime or a composite number. So according to this theorem, it tells us that the product of prime that we are talking about, that is unique in nature. That means you cannot have any other product of such kind, which when you multiply them give you the integer back, right? And this product is unique, except that the order in which prime occur, they could differ. For example, suppose we are taking some number which is a product of prime. So you take 2 into 3 into 5, say. So 2 is a prime number, 3 is a prime number, 5 is a prime number, right? So it is what? It is equal to 30, right? Yes. So you could write 30 as also 5 into 3 into 2, or you could write 30 as equal to 5 into 2 into 3, and so on. So here the product is unique, right? You are always writing 2, 3 and 5 as the primes by which their multiplication give us 30. However, the order may differ. So writing it in terms of alphabets, it is, suppose the number n that we have taken was 30, so n could either be written as p1 p2 up to pr, and it is also written as q1 q2 up to qs, right, where both p and q, they are prime numbers. Then this order, this has to be the same. Here in the given example, we are taking first, second and third prime. So here also we are taking first, second and third prime. So here also we are taking first, second and third prime. So basically the order here, the number of primes that we are taking, that is same. So r is equal to s. And after renumbering the q's, so that means after reshuffling them, you will again get pi is equal to qi, because the primes are basically the same. We have 2 everywhere, we have 3 everywhere, and we have 5 everywhere. So this is what this theorem say, right? Now next, let us move on to this concept of least common multiple. Now what is this least common multiple here? It is, suppose you take 2 non-zero integers a and b, right? So we are taken a and b. So whatever now next is you take their common multiples. Now whatever is the least among them, that would be the LCM of those numbers, least common multiple, right? So for an example, let's take 2 numbers 4 and 6. So we first of all have to list down their common multiples. So what are the common multiples? The numbers which are divisible by 4 as well as 6, right? So 12 here is a number which is divisible by 4, right? because 4 divide it by 3, and it is also divisible by 6 because 6 divide 12 by 2, right? So next we have 24 as the number which is divisible both by 4 and 6. Next is 36, next is 48, and the list is countless. You could keep on writing the numbers like this. So what is the least among this number? That is 12. So 12 would act as the LCM of 4 and 6. Right, again you see the LCM of 4 and 8, that is 8, because here in this case the common multiples are 8, 16, 24 and so on. So this is these are few of the properties of integers. Next we'll be looking at another concept which would strengthen our basic for studying this subject of group theory. So I hope you understood this these concepts. Well, that is it for this video. Thank you for watching.